We're going to be trying to picture our gas molecules on a molecular level and get an idea of what they're like, what they tend to do. We have a theory called kinetic molecular theory that helps us picture what our molecules are doing. These are things that we are generally going to assume to be true about a gas, particularly what we call an ideal gas. Number one, gases are composed of molecules that are in continuous motion. They're always moving around. They're traveling in straight lines, and they only change direction when they collide with other molecules or the wall of a container. They go in a straight line, then they bump into things, then they go at a new angle, but still a straight line, similarly to billiard balls. Number two, molecules are small compared to the distances between the molecules. There's a lot of empty space in between gas molecules, and the molecules themselves are so much smaller compared to that empty space that we can assume that they're negligibly small. We don't take into account the size of the molecules in most calculations. Number three, pressure is a result of collisions between gas molecules and the walls of their container. As the gas molecules bounce off of the sides of their container, that's creating pressure on the container. Number four, gas molecules exert no attractive or repulsive forces on each other or on the container walls. So when they collide with each other or with the walls of their container, those collisions are assumed to be elastic, which means that there's no loss of energy as a result of the collision. They bump into each other and they go away from each other with the same energy that they had going into the collision. Number five, the average kinetic energy of the gas molecules is directly proportional to the Kelvin temperature of the gas. The higher the temperature in Kelvin, the more kinetic energy the gas is going to have. We're going to think about the gas laws we talked about at the beginning of the chapter in terms of what the atoms and molecules are doing. If we heat something up, that is adding energy to the molecules. The molecules have an increased kinetic energy, which means they're moving around faster. That faster movement means they're more likely to bump into each other, and they're also more likely to bump into the walls of their container. Having more collisions is going to result in a greater pressure because the gas is bumping into the wall of the container more. This leads us to Daltons Law, which says that as the temperatures increase, the pressure will also increase. Pressure and temperature are directly proportional. We can also relate kinetic molecular theory to Charles's law. Charles's law tells us that volume and temperature are directly proportional. Let's say we have a container with a piston that can move up and down. And at the beginning, the gas pressure on the inside equals the atmospheric pressure on the outside. If we increase the temperature, that's going to make the molecules inside collide more. And as they collide more, there's going to be sort of a temporary increase in pressure. So the gas is going to push the piston upwards. Since the piston is movable, the container's volume expands until the gas pressure equals the atmospheric pressure again. Therefore, heating up the molecules ends up causing an increase in volume. We can also think of kinetic molecular theory in terms of Boyles Law. Boyles Law tells us that pressure and volume are inversely proportional. Let's say we have a container with a piston and we push the piston down with force. As we decrease the volume, more collisions occur because the gas molecules have less space to move around in. They're more likely to bump into each other, and they're more likely to bump into the walls of their container. Because there are more collisions, there's increased pressure. Therefore, decreased volume leads to increased pressure. We can think about kinetic molecular theory with Avogadros Law. Avogadros Law tells us that moles and volume are directly proportional. If we increase our number of moles of a particular gas, that should increase the frequency of collisions, which should increase the pressure. But again, if we have a piston that's able to move, or let's say it's in a balloon that's able to expand, if pressure is held constant, the volume is going to increase in order to compensate for that increasing number of moles and the resulting increase in collisions. We can also look at kinetic molecular theory and Dalton's law of partial pressures. We've mentioned as one of the postulates of kinetic molecular theory that the gas molecules are very small compared to the empty spaces between them. There's a lot of empty space that other gases can sort of slip into. So when we mix different gases together, They're just going to fill in some of that empty space. Because they're so small compared to the empty space, it's really as if they're not even there in terms of how it affects the frequency of collisions and therefore pressure of the other gas. That means that the total pressure is just the sum of the pressures of the individual gases. I encourage you to go to the slides and click on the link that says PhET Gas Simulator, or you can Google search PhET, and there's a really great simulation of gas molecules. So you can see what happens when you change molecular masses, change different temperatures, and really get a mental picture of what's happening on a molecular level.